Any questions about anything from last time? Yeah.
So the Poisson kernel formula for U is not really useful for actually calculating things, right? It seems pretty arduous to work with.
I'm going to convince you, I hope today, that it is useful, and the convergence is fast enough that it's a useful thing. Of course, you calculate that integral, you have to do it, chances are you'd have to do it numerically, because you would, which is not a big deal. So it would spit out numerical solutions to these problems pretty nicely, especially far inside the disk. There'd be some more subtle questions about getting really close to the boundary, because then I'm going to explain why getting really close to the boundary is delicate today. Anyway, we've been working on the heat problem of finding the steady state temperature in a circular metal plate, knowing the boundary on the edge. Okay, so and the solution physically is we're looking for a function that's continuous up to the boundary on the whole region. It needs to be differentiable enough on the inside so that we can compute the Laplacian has to be 0 inside. So, in fact, on the inside we want the function to be C2 smooth with those first and second partial derivatives that come into the calculation of the Laplacian. Those are harmonic functions. That's the definition of a harmonic function. Laplacian is 0. And we want the function in polar coordinates, when the radius is 1, we want u of 1 theta to be equal to a given function. That's the temperature function on the boundary. That's the classic Dirichlet problem. And funny, Poisson was the thesis advisor for Dirichlet. So, kind of the family business. Well, last time we used separation of variables and the basic Fourier series techniques to come up with a solution to the problem. There it is. It looks exactly like a Fourier series. The only thing different now is that there's r to the n's next to the cosine n theta and the sine n theta. And those r to the n's actually make that series converge very rapidly, because when r is less than 1, r to the n goes to 0 really fast. So in fact, those things converge better and faster than regular Fourier series do, because of those are like geometric series killing the tail end of that series. So they're very rapidly converging. That's when r is less than 1. When r starts getting close to 1, well, it's not as rapidly. It still goes to 0 well enough to estimate it using geometric series, but it's just not as fast the bigger r is. And when r is equal to 1, then it has all the delicacy of Fourier series. And we know that Fourier series don't exactly, it says Stein has the example of a continuous function whose Fourier series does not converge to the function at a point. So if r was equal to 1, that would be the same delicate problem of convergence of Fourier series. We're going to see that r really makes things work fast and nice. Okay, so remember the a's and the b's are just the Fourier coefficients for the f of theta function that's given. Okay, well, that's the solution we came up with. I started playing around with it last time and changed that formula into using complex coefficients. So when I did that and played around with it, and noticed that if I take the sum, that would be those partial sums would be the sum from little n going from 1 to capital N. And if I let that that partial sum in complex form is inside the brackets right here. And so that thing up there would be the limit as capital N goes to infinity of those partial sums. An interesting thing, when I write them in the complex form, when I have a positive n, it's r to the positive n e to the I n theta for the function times the complex number Cn, which are the complex Fourier coefficients. And when that n is negative, well, then it would be an e to the minus I something theta, but it would be r to the absolute value of that negative number. So you see that first sum in the bracket is the sum as n goes from minus n to minus capital N to minus 1. Those are positive powers of r also, even those are negative n's there. So they go to 0 fast that way. If it was 1 over an r to the n, that would be a bummer, because that would have bad behavior at the origin. But it's not. It's that. And then I cleaned that stuff up and stuck it under 1. Let's see. Then I wrote out the coefficient Cn as an integral with respect to t, and cleaned it up and was able to write that thing inside the bracket as an integral against a function.
Are we missing ft?
Yeah. I thought that felt weird. Sorry. What am I doing? Right, the ft belongs right here. Right, so that happened after I wrote the CNs as integrals with respect to t by their definition, and realized, I can shove that e to the minus int inside my thing there and have the f of t pulled out like that. And I stared at that for a second and realized those are geometric series. And because of the r to the n's, they converge very quickly. So let me show you. I was going to skip this calculation, but I'm going to go through it quickly here. So if you care about it and want to check it yourself, it won't be hard to do. I'm trying to convince you also that it's not hard. So I'm going to split that sum there into two pieces. The sum of the positive ones, n going from 0 to capital N, and then the negative ones. That would be minus n to minus 1. Okay, and so when the sum is 0 to n, if I let w be e to the I theta minus t, that r to the n times e to the I n theta minus t is the nth power of r times e to the I theta minus t. Okay? So that sum of the positive ones is 1 plus r times that w. The w is right here. E to the I theta minus t. Plus, etc., all the way out to r times w to the n. Okay? And that's a geometric series. We have a formula for the sum, and it's 1 minus rw to the n plus 1 over 1 minus rw. And because the r is less than 1 in absolute value, and the w is modulus 1, so that number rw has modulus r. That goes to 0 very rapidly when you take it to the n plus first power. So as I let n go to infinity, that's going to rapidly zoom into that green box there, 1 over 1 minus rw. And the negative ones, I'll write w conjugate, that would be, the conjugate of that thing is e to the minus I theta minus t. And so it's a very similar looking thing, except I've got W conjugates, where the W's are, and it starts from 1 instead of 0. So I write out that sum and realize, I can factor out an RW bar from that mess. And then I get something that looks like a geometric series in the square brackets, except it goes out to RW bar to the n minus 1. And so when I use the formula for the sum of that geometric series, it'd be n minus 1 plus 1 power, which is just the nth power. And the RW bar stays in front there. So I get RW bar times 1 minus something that goes to 0 rapidly over 1 minus RW bar. So if I let the n go to infinity, that one sums up to RW bar over 1 minus RW bar. And now I add them up. That would give me the sum from minus infinity to plus infinity. So that'd be the sum of those two green boxes. First one plus the second one. And I said it was clever algebra. Well, it's just absolute bonehead algebra. I cross multiply and add those together. And that's what I get. On the top, when I cross multiply and add them together, notice the terms RW bar are there cancel each other. So these two right here cancel each other. And W times W conjugate is 1 because W is e to the I something. So the modulus of that would be involve a cosine theta, a cosine angle squared plus sine squared, which is 1. That's a point on the unit circle, so it has modulus 1. So those cancel, and then I'm left with minus r squared times 1. That's the thing that's supposed to be on the top, namely a 1 minus r squared. And you look at the thing on the bottom and say, aha, that second one, when I multiply, is the conjugate of the first, because r is a real number. And when you multiply a conjugate by a complex number by its conjugate, you get the modulus squared. So that simplifies to 1 minus r squared over modulus squared of 1 minus rw, which I've written out there. And that's not quite what I wrote for the Poisson kernel. I can multiply that thing by 1 in the form of 1 over e to the it modulus squared. That's 1. And when I distribute that e to the it squared through the denominator, I get the famous formula for the Poisson kernel. And it zooms into that very rapidly because the tail end of those series are going to 0 so rapidly. So that I get this new formula for my solution to the problem in terms of the Poisson kernel. There it is. Where the Poisson kernel, I got to put the 1 over 2 pi back in. There it is. The Poisson kernel is that thing. Okay, so there's the details if you're dying to see them. Interesting, you draw this picture here. There's an e to the it going around the unit circle. There's an r e to the I theta, that's that green point. That distance there is from 0 to that point is r, that's the radius in polar coordinates. E to the it is on the unit circle, so that red radius is 1. And the distance there is the distance from e to the I, that's d, the black line. That's the distance from e to the it to r e to the I theta. And the angle there, let's see, that would be theta minus t. If that was a right angle, I could use the Pythagorean theorem. And I'd have d squared as 1 squared plus r squared. When it's not a right angle, then the famous law of cosines modifies the Pythagorean theorem. So it's the correction term for using the Pythagorean theorem. D squared would be 1 squared plus r squared minus this correction term, which is 2 times this 2 times the product of the sides times cosine theta minus t. So that'd be 2r cosine theta minus t. I guess to emphasize, if that other side wasn't 1, you'd see it right here. 2r times 1 times cosine theta minus t. And so another famous formula you'll see in books of the Poisson kernel is that you can write it completely in terms of real things, like that. And the thing in the denominator comes from the law of cosines. That's the formula you'll see in all the books. I like my formula because it's geometric and you see the sort of relationship between the points nicely. And in fact, it's going to make my next result quite straightforward to demonstrate. Questions about it? Yeah.
Should we be concerned when r is equal to 1?
Well, that's where all the... when r goes to 1, then you get 1 minus r squared, and the top is identically 0. So it looks like, oh my gosh, the Poisson kernel is just going to be 0 when I'm on the boundary. But it's interesting. It's going to be like a good kernel. It's going to have a humongous peak. And eventually it goes to 0 everywhere. It's going to be like a delta function. So after people started understanding this thing, that's when it was the time for the delta function to be invented. Because that Poisson kernel on the actual circle is like the limit of a delta function. And you're going to see that in the next calculation I do. The Poisson kernel has all the properties of a good kernel in the sense that Stein calls good kernels. First of all, it's strictly positive. When when the radius is less than 1, the Poisson kernel is strictly positive. And my formula makes that clear, more clear than the law of cosine formula, because everything in it is positive. And the second good property a thing should have is that when you look at the area under that curve, it's 1. So if I'm not integrating against the f of t there, I'm integrating against nothing, just 1. The area under the Poisson kernel in the t variable is always 1. And that's whenever, for any theta, and r needs to be less than 1, and any theta. And that's an easy thing to check. Let's see, the y is, all my partial sums there? Let's see, so here's the y. Remember this integral. Remember those partial sums integrate. They converge uniformly. So in fact, this integral from 0 to 2 pi of that thing is the limit as n goes to infinity of let's see, there's a constant term. The constant term was 1 over 2 pi times 1. And then the other terms would be a plus of the sum n unequal to 0 and the absolute value of n less than or equal to n of integrals of something. Oh, let's see. What did I have? I'll put them back in here like this. Cn I'm sorry, the Poisson kernel didn't involve any CNs. It involved r to the absolute n, e to the I, nt, dt. And it'd be 1 over 2 pi here. And those are all integrate to 0. Because of cosine nt and sine nt, you integrate from 0 to 2 pi. They have just as many humps above the axis as below. And so they cancel, and you get these are all 0. We did that calculation when we were looking at the Dirichlet kernel. And this of course is this is 1. So that's where the 1 comes from, is the constant term, which is the averaging term. Okay. So that's a no-brainer based on the fact that it's the limit of a sum that has that property. Okay, now the third property is that it has that good kernel property of having a great big bump. And in fact, it's going to have a great big bump. I'm going to draw the picture here and show you. Let's see, I'll draw a circle, big circle. Here's my e to the I theta naught. Now I'm going to draw a little circle of sides delta about this. So this green circle has radius delta. And now I'm going to draw a purple circle that's going to have radius delta over 2. And the place of interest is going to be this little shaded region here. I'm going to stick my, in here is going to be my point, r e to the I theta. So that point right there is going to be r e to the I theta. Inside that little thing of radius delta over 2. Let's see, I should make this look nicer. Okay, that's has delta, and this thing right here is e to the I theta naught. Okay, that's the picture, and I'm going to make this part of the circle here. It starts outside that the green circle of radius delta. Okay, this is the unit circle. Okay, so let's see. I'm going to define a set I sub delta. Those are going to be angles. Those are going to be the angles t such that e to the it on the unit circle is not in the disk of radius delta about e to the I theta naught. Okay, that's the picture. And this fact I'm telling you about is that the Poisson kernel goes to 0. So P r theta t goes to 0. Not only goes to 0, but it goes to 0 uniformly. That's important. when t is in that red stuff. When e to the it is in that red stuff. So this red stuff is in e to the it. And the I delta is the angle such that you're in that red zone. And as r goes to 1. So r is going to increase to 1, as in that picture. As r goes to, let's see, I want to say r last. So when t is in there, and r e to the I theta needs to be in that little dip, like I pictured it, the disk of radius delta over 2, about e to the I theta naught. And the uniform convergence is as r increases to 1. All right. That's a very simple proof from looking at the formula and that picture. So I'll do it right here as long as I got the space. Let's think about it. P of r theta t is 1 over 2 pi, 1 minus r squared, and then we'd have r e to the I theta minus e to the it squared. Okay, and let's see, what's going to make it to go to 0 is, on the top we have, that's a 1 minus r times a 1 plus r. It's the 1 minus r that's going to make the uniform convergence. And on the bottom, if you think about, my r e to the I theta is stuck inside that purple circle of radius delta over 2. And my e to the it is going around that red stuff. And those never get very close together. In fact, the closest they ever get together is theta, delta over 2. So this is an r e to the I theta minus e to the it squared this modulus thing is always, so whatever, the modulus of that thing is always greater than or equal to delta over 2. Okay. And this thing, 1 plus r, is less than 2. And so when I estimate this positive thing, I get that it's less than 1 over 2 pi times 1 minus r times 2 over delta squared. Delta over 2 squared. So that thing right there is, let's see, the 2's cancel. I got a 2 squared. That's 4 over delta, pi delta squared times 1 minus r. That's just a number, and I can make it go uniformly to 0 on that interval by taking r close to 1. So sure enough, that does go to 0 uniformly as r increases to 1. So it's a very straightforward geometric picture to look at. Questions about that? Okay, so what does that mean? It means if I graph my Poisson kernel, here, let's suppose my theta naught is right here from 0 to 2 pi. if r is not so close to 1, it might look like this. Kind of a mild bump. There'd be a bump. This one would be r not close to 1. But when r gets close to 1, then it would be really small, and then boom, it'd be like a delta function. So that would be r close to 1. And the area under both those curves would have to be 1. So the area under both curves is 1. Okay, so I'll make some area here. That area is 1. So it means the area is really concentrated near theta naught. That's very much like it happened in the Fayers with Fayer kernel. Had that big bump, and the bump got very concentrated near the point of interest. And that's the key to what good kernels do. So in fact, well, let's see, there's one more property I need to mention. Number 4 is you can if you take the Laplacian of my Poisson kernel in polar coordinates, that's identically 0 for each t. So let's see, here we would need 0, less than or equal to r, less than 1, and any old t. That means you can take the, well, because the thing converges so nicely, it's not a hard thing to show that you can differentiate under the integral sign. We can take the Laplacian with respect to r, in polar coordinates under the integral sign to see that the formula spits out a harmonic function, to see u of r theta that we get from the Poisson formula is harmonic. Inside the unit disk. Or I just should say in. So, the last thing to show, if you're going to show that we have a solution to the Dirichlet problem, is you want to show that because of these, now it's easy to show u of r theta tends to f of theta as r as f of theta naught as r e to the I theta tends to e to the I theta naught. Okay, so here's the demonstration. We've seen exactly this before, so it's always good to see this argument again. So let's see. I have my u of r theta is defined by the Poisson integral. It's the integral from 0 to 2 pi of p of r theta t f of t dt. And so u of r theta minus f of theta naught, I'd write that same thing down again, but this time I would use the fact, let's see, so I'll leave my u of r theta there. And then I'm going to write f of theta naught as 1, but guess what? 1 is going to be in the form integral from 0 to 2 pi of just the Poisson kernel, dt. Okay, I just wrote 1 in a crazy way, times f of theta naught. And when I look at those two things, I realize, oh my gosh, they look so similar. And in fact, since this is a constant, I can pick this up and stick it in that integral. Okay, so I'm using one of the key properties of a good kernel when I do this. This, now I see, is the integral from 0 to 2 pi of the Poisson kernel, r theta t. And now I can put in here f of t, that would give me the first u of r theta function, minus f of theta naught, dt. Okay, you stare at that for a second and realize, oh, the Poisson kernel has this great feature that it's getting really small on a big set. Okay. And so we're going to split this integral into two parts. The part where the Poisson kernel is really small, and the other part is where the function f of t minus f of theta naught is really small. And that's going to be the key. By splitting it into two parts, and we're going to be able to show that both those parts get small. So let's see, I should maybe start taking the absolute value of this mess. Put green absolute values. And let's see, that thing inside there, that would be, have a green absolute value. This would be an integral along I delta plus the integral from theta naught minus that delta to theta naught plus delta, or plus an angle like that. Okay. And the reason that's a brilliant idea is that the Poisson kernel is small here. And the other term, f of t minus f of theta naught, is small on this one. And hopefully, when we add them up, we're going to get something small. Okay, so let's see, to do it carefully, let's see, let's let epsilon be bigger than 0. Since f is continuous, I can get so there exists a delta bigger than 0 such that absolute f of t minus f of theta naught is less than epsilon over 2, make it, like we did in the Fayer theorem, when t minus theta naught is less than delta. Okay. Also, f is continuous on a closed interval, so it's bounded. On minus pi pi, so bounded there. Say that the absolute value of f is less than m on the whole interval. So that means that f of t minus f of theta naught is less than f of t plus f of theta naught is less than m plus m equals 2m. Period. Okay, that's going to be small on a little delta thing. On the rest of it, at least it's not going to be bigger than 2m. Okay, so let's. I've got my integrals again. I've got the integral on I delta plus the integral from theta naught minus a little bit to theta naught plus a little bit. That's going to be less than or equal to the integral of I delta. Let's see, here's where I got to use the fact that the Poisson kernel is positive. Normally I'd put an absolute value around this thing, but it's a positive thing. And here I have to put absolute value dt. So important that the Poisson kernel is positive here, so I don't have to have an so I can do that. So P is positive. So check. I don't have to put an absolute value there. And this thing is less than 2m. And I've got the other one plus the integral of theta naught minus delta to theta naught plus delta. Same stuff. Different reasons. Okay, let's. I'll call this first one I1, integral number 1, and this second one, integral number 2. There's going to be two different reasons why these go to 0. Okay, I1 is maybe the easy one. We get that estimate. I1 is less than or equal to the max of the Poisson kernel on I delta when t is in I delta times 2m times the length of that those intervals times the length of I delta. That's the length in 2 pi. It doesn't fill out the whole 2 pi thing, but it fills out a lot of it. But whatever that is, that it's less than 2 pi. So I get 2m times 2 pi, and then the max of that thing goes to 0 uniformly. So the aha is max goes to 0 uniformly as r increases to 1. So we're done with the first one. We can make it less than epsilon over 2. Okay. Now I2 is interesting. Let's see. I2, the Poisson kernel is not small there. That's where the bump is. So I think, oh my gosh, there's a great big bump there. There's no way that's going to be small. Okay. And of course that puzzled people who started using these things for a while. The key is that even though the bump is gigantic, the area under it is just 1. So watch this. This is an important calculation. This would be less than or equal to, I think I'm rewriting the same stupid thing, but plus delta PR theta T epsilon over 2. Right? Go back there. That f of t minus f of theta naught, in that little sign delta interval, that's where that's less than epsilon over 2. And that's right where the big bump is. But when you realize, oh, because that Poisson kernel is positive, this is going to be, so this is a brilliant idea. That's less than the integral on the whole stupid interval. Because the Poisson kernel is positive. And I can pull the epsilon over 2. Oh, I won't do it yet. And that's equal to epsilon over 2 times 1. So the other one's less than epsilon over 2. I make r getting close to 1 to make the first one small, and then this one is just small. Yeah, let's make it go 0 to 2 pi, the whole interval. Because it's periodic, I could also do minus pi to pi, like kind of look like I might be doing. So we're done. So that's one of the key features of a good kernel is, even though it's gigantic there, the really delicate spot where I care about, the integral is 1. The area under the curve is 1, and that allows me to control that little piece. So this is one of those events where, we use separation of variables and all kinds of wild and crazy things that maybe we'd have a hard time convincing somebody that it's a proof. But then we get this formula. And you get this formula in front of you that you can analyze like this and demonstrate that, oh my gosh, it does work. So all that wild, crazy stuff paid off, and that we got a very concrete thing that does what we want it to do. And that argument comes up again and again in analysis, the good kernel business. Let's see. I thought maybe Friday I'll do some odds and ends that are kind of fun to do. Next time, I'll do some odds and ends. Including a very easy, a fun and easy demo that Fayer's theorem implies the famous Weierstrass theorem. So Fayer's, I forgot how to spell Fayer, F-E. The famous Weierstrass theorem that polynomials are dense among continuous functions. And I'll explain exactly what I mean by dense among. It's the thing you learned in Math 341, are dense among continuous functions